Hi, in this video we're going to show you how to calculate the bending moment for a simply supported beam. So this applies to all simply supported beams, but in this example we'll use a short span bridge. And in this we'll be going through three things. First of all, we'll use first principles to calculate the bending moment from a uniformly distributed load, such as the deck self-weight. Then we'll look at the bending moment from a point load applied at any point in the span. And then we'll look at the combined uniform load and point load, and we'll show you how to work out where the maximum moment occurs, and then we'll look how to calculate that moment.
Okay, so what we're going to do first is draw a simple diagram of that bridge, which is going to be two supports and a simple line to represent the deck. That bridge will have a span that we're going to call L, its length. We are then going to apply a UDL onto that bridge, which is a uniformly distributed load, and I'm going to use this squiggly annotation, which is what I've always used in my career. Different places may use different ways of representing that, but that's fine. And what we're going to do is we're going to give that a unit, which is that UDL is going to be W kilonewtons per metre. Those are units I'll be using, but obviously you may use different depending where you're from. So the total load on that is equal to, on that bridge, is equal to WL, which is the UDL in kilonewtons per metre, multiplied by the length in metres, which gives you a total load in kilonewtons. Some people prefer to do this in using total loads, which in this case I'll call a capital W, or uppercase W, rather than using the lowercase and the length. I prefer to break them down into length and UDL. And the reactions at this bridge are R1 and R2, which are very simple to call up because we've got a bridge that is simply supported. It has a UDL on it, which is evenly distributed across the whole length. So reaction at 1 is going to be equal to the reaction at 2, which is half the total load on the bridge, which is therefore WL upon 2. Okay, so we're now going to go into the shear forces. Okay, and strictly speaking, we don't need to talk about shear forces here because we have a simple exercise. But when you get to more complicated load arrangements to look at, there's a really useful part for shear where something known as the point of zero shear, which is where what you can use to determine where your maximum bending moment occurs. We do use that later in this lesson when we're combining lots of various load cases. So let's put that UDL back on, and what we're going to do, because we are in equilibrium, then the shear at the end is equal to the reaction. So we have a shear force here of WL over 2, and that will drop as you move along the bridge. And so if we, in this example here, if we assume that that's a distance A from the support, then that at point A, the load has dropped from WL upon 2 by the amount of load in that area, which is equal to WA in this instance. Now, you don't really need to remember that for getting to our mid-span results, but that just explains how that force drops off and it keeps going, and we end up with minus WL upon 2 at the other end. Now, a nice check that you've got everything right is on this example is you'll see that that is equal to WL, which is the total load on the bridge. Okay. The other thing to note is that you have a point of zero shear is at midspan on this instance. Okay, so we're now going to go on to look at the bending moments, which is what we're focusing on. Okay, and let's underline that. Right, and we'll draw our bridge simply again, okay, which has got the span of length L. It has got a UDL on it of W. It has the reactions of WL over 2, reaction of WL upon 2, and at midspan we are a distance of L upon 2 from the bridge, okay, from the support. So to work out the bending moment at a particular point, you're resolving all the bending moments to the one side of that line. So we could resolve to the left of that midspan and we'll come to an answer, or we could go to the right of the midspan and resolve forces there, but you'll come to the same answer. It doesn't matter what part of the bridge you look at, it will come to the same answer. So we know that the bending moment is equal to the sum of the force times by distances. So in this case, our force that we first look at will be the WL upon 2 reaction. Okay, so we'll put equals, right, do that better, WL over 2 multiplied by a distance which will be that distance. We're L upon 2 from the middle of the bridge. So we are therefore times by L upon 2. Okay, and then we then have to subtract from that the moment acting in the opposite direction due to this area that I'm shading. So this area here that's shaded blue will have a total load of WL over 2. Let's redraw that a bit. Okay. So let's type that in again. That is W times by L over 2. So the total force acting in the other way is going to be equal to WL over 2 times by a distance. So that distance is going to be from where the centroid of that load acts, which is going to be that distance, which in this case will be L over 4. So your total bending moment is therefore WL squared over 4 minus WL squared, minus WL squared over 8, which is equal to, and this is the key one, this is equal to WL squared upon 8, or WL upon 8. If you look at some textbooks, we'll use that. So that is a bending moment that for simply supported span that you will remember for your whole career. So let's just remove some of this text for a minute, some of these calculations, because you don't need them. Okay, and we'll get rid of some of this, just give a bit of space. So again, remembering that we have got this WL squared upon 8, that happens at the midspan. If you go through those same calculations in exactly the same way, but at a distance anywhere across the support, you might want to do it at this, wherever it is, and you just plot that as a series of results along the length of the beam, you'll ultimately end up with a shape like that, where that is your bending moment diagram for a simply supported bridge, which is equal to WL squared upon 8.
So now we'll look at the bending moment from a point load. And as the vehicle moves along the bridge, you'll see that the bending moment profile changes as additional axles go onto the bridge. And the more axles that we have, the closer we get to a curved profile. But we'll keep it simple and we'll focus on a single point load. The same principles apply, whatever the arrangement.
Okay, so we're going to go through exactly the same again, but this time for a point load. We'll do it quicker because you don't want to hear me talking too much, and it's a bit more straightforward. So we're going to have the beam again with a distance, a span L. We're going to apply a point load this time of P. It's going to be a distance A from support 1 and a distance B from support 2. And we're going to have our reaction R1 and our reaction R2. So first thing we're going to do is determine the reactions, and this is pretty straightforward. So we're going to go through, and to do that, we're just going to do resolve forces around R2. So we're going to resolve around R2. Okay, and this is going to be formula number 1. There's going to be a simultaneous equation. So we know that the resolving around there, we've got 0 moment at that point, therefore the sum of the bending moment caused by that force at a large lever arm from support 2 is going to be equal and opposite to the bending moment caused by that force at a smaller lever arm. So we know that R1 times by A plus B is equal to P times by B. So therefore R1 is equal to PB over A plus B. Now formula 2 is quite an obvious one. You know that the total force applied is equal to the sum of the reactions, so is equal to R1 plus R2, which means that you can then determine from those two formula that R2 is equal to PA over A plus B. Okay, and that makes sense because R1, P is closer to R1, and so it's multiplied by the bigger value of, it's got PB, and R2 will be smaller, that's why it's multiplied by A, because it's further away from the load. So just putting those onto that, we've got R1 is equal to PB over A plus B, and R2 is equal to PA over A plus B. Okay, and then we can get rid of all that working out, you don't need to see that. So next is, while I'm scribbling this out, we'll move on to shear forces. Okay, so we're going to do shear force diagram, SFD. Okay, so what we know here is that the forces are going to be balance each other out. So we've got PB reaction over A plus B, and we've got PA over A plus B. Okay, and we know that because we've got this equilibrium, we know that at that support we have got PB over A plus B. Okay, well, just for, don't need to, but let's put the shear force P in. Now, because there is no load supplied between the support and point P, that shear force doesn't change. It comes across. Okay, then you get to P and it will drop by a value equal to P. Okay, and because there are no loads applied between P and support 2, it will come across at the same value, at the same level, and you'll then get a value of shear force of that of PA, or strictly speaking minus PA over A plus B. So let's quickly put that up over here and out of the way. I'm going to draw our shear force diagram very quickly. Okay, and it is that it's a shear force for a point load PB over A plus B, PA over A plus B. Okay, and we can now get rid of all this gunk and we can start to look at how to do our bending moment diagram. So again, the bending moment diagram is very simple. Okay, sometimes referred to as a BMD. So we're going to draw the bridge again. We're going to draw point load P. We're going to put dimension A, dimension B, and I'm going to put the reactions in again. PB over A plus B and PA over A plus B. Okay, so we know that a moment at any point is equal to the sum of forces times distance, and we can do this in two ways. We can either, starting at the point P, we can resolve forces to the left of that, or we could around using the reaction from R1, or we can resolve to the right using the reaction from R2. You get exactly the same answer, as it was equal to the force that you're going to get. The moment you're going to get is going to be equal to this force, which is PB over A plus B, multiplied by the distance of that force from the point you are looking at. So it is point multiplied by A, which is equal to PAB over A plus B. So that is fairly straightforward, and if you were to check that at various points along the beam, you will find that you've got a bending moment, something like this. Should have drawn that in green, but never mind. That is PAB over A plus B. Okay, and then just purely because you need to know it, let's show you what happens if that was at midspan. Right, 2 more seconds. Let's just, if this was a midspan, and then you've got a point P applied that is equally positioned from the two supports, then your bending moment there would be bending moment equals PL over 4, and just like the WL squared upon 8, that is a formula that once you know it, you will know it for good. Okay.
Now let's have a look at the combined effect of both a uniform distributed load and a point load. So for the UDL on a simply supported bridge, we know that the maximum moment occurs at midspan. We also know that for a single point load on a simply supported span, the maximum moment occurs where the point load is applied. However, when we combine a UDL and a point load, it's less obvious where that maximum moment is. In the example that follows, the maximum moment occurs at neither position, so I'll show you how to work out where the maximum moment occurs and then how to calculate that moment.
Okay, so let's do that again, and this time we'll use real values. I'm going to take a beam that has got a span of 10 metres, simply supported, so it's got a pin at each end. It's got a UDL on it, which we will call 5 kilonewtons per metre. It has got a point load of 20 kilonewtons, and that acts at 3 metres from the support. Now the reason I've given you these values is on a simply supported bridge with with sort of no moment restraint, so it's simply supported. The maximum bending moment due to UDL is at the middle. The maximum bending moment to a single point load is at the point of the point load. So where in this scenario will be the maximum bending moment occurring, and this is where we go back to the point of zero shear, which I've mentioned many times, and this is where it really comes to understand it. So let's start with reactions as we always do. Okay. And I'm going to call this R1. I'm going to call this right hand one R2. And what I'm going to do to start with is resolve around R2. And just very quickly, we know that R1 times by 10 metres will be equal to the 20 kilonewtons multiplied by 7 metres from R2 minus the 5 kilonewton metres over a 10 metre length multiplied by 5 metre distance to the centroid of it. If we look at that as a simultaneous equation, well, the first equation, we're saying that R1 times by 10 metres is equal to 5 kilonewtons per metre times by 10 metres times by 5 metres. Okay, add 20 kilonewtons times by 7 metres. So what that means is R1 is equal to 250 add 140 all over 10, which equals 39 kilonewtons. Now, simultaneous equation, point 2, we know that R1 add R2 is equal to 5 kilonewton metres times by 10 metres, add 20 kilonewtons. So the total for applied force is equal to the total reaction. So R1 and R2 is equal to 70 kilonewtons. So R2 equals 31 kilonewtons. So you can obviously pause if you want. I'm just going to go through it quickly. So R1 is equal to 39. If that looks like a 9, great. And then that one is equal to 31. And we'll quickly delete all this and we'll show you the shear force. This is the important bit to understand where the point of maximum shear is. Zero shear is. Okay. And I'm going to draw this a bit bigger. So we're going to do a big, long span. That's 10 metres. And this will be the midspan. And this will be 3 metres away. So we call that 3 metres. We call that 5 metres. Okay. So we know that we've got 39, sorry, put it in a different colour, we've got 39 kilonewtons over here, we've got 31 kilonewtons over here. We know that the shear force is a pin on a simply supported structure, it's not continuous. We know that the reaction there will be equal and opposite, so that's 30 kilonewtons. And what will happen is, because we've got a UDL, we've got a linear reduction in shear load as we go along here, and that reduction is going to be equal to 15 kilonewtons. And where does that come from? Well, that is the total force in that area there, which is a 3 metre length multiplied by 5 kilonewtons per metre, which means at that point there, you will have, you'll have 24. Okay, and let's delete this. And because we have got a 20 kilonewton point load, there'll be a sudden drop in the shear at that point, and that'll go from 24 to 4, because that's the 20 kilonewtons. And we then know that we've got a UDL all the way to the end, so that is going to go down linearly all the way to 31 kilonewtons at the end. So what we need to understand is what that distance is. That's where the maximum bending moment will have, because that's your point of zero shear. And it's quite straightforward really in this to do it in your head, because you know you've got 4 metres, the load's dropping off at 5 kilonewtons per metre, so it's another 0.8 metres before we get to the point of zero shear. So call that 3.8 metres. So I'll delete that very quickly, and we will add in there just a quick note to say point of zero shear. Let's do it so you can read it. Point of zero shear equals 3.8 metres from R1, and apologies for my writing. Okay, then what we're going to do now is we're going to do the bending moment, which is what it's all been about. And we'll start by drawing that, and what we're going to have, that's a 10 metre span, and this point here is going to be at 3.8 metres, where we know the maximum bending moment will happen. We know that we've got 39 kilonewton load here, reaction. We know that we've got a 20 kilonewton point load applied at 0.8 metres from where the maximum moment is. And we also know that we've got a 5 kilonewton per metre UDL, of which this area here is, if you imagine you've got a load of 5 kilonewtons per metre over 3.8 metre length, that with its centroid will be 1.9 metres from our point of zero shear. So we can therefore do a sum of force times distance at the point we're interested in. So if we do M is equal to the sum of force times distance, which for 3.8 metres from R1 will be 39 times by 3.8 minus 5 kilonewtons per metre times by 3.8 metres times by 1.9 metres and minus 20 kilonewtons times by 0.8 metres. So again, pause if you're struggling to keep up. So that is equal to 148, just rounding, minus 36 minus 16, which is equal to 96 kilonewton meters. And that is acting at 3.8 meters from R1. So there you have now worked out with a point load and a UDL how to work out where the maximum moment occurs and how to calculate that moment.
Okay, so a quick summary then. First of all, let's imagine a simply supported beam where you know the position of maximum bending. That's quite easy. For example, a UDL, you know it's at midspan. For a point load, you know it's where the point load is applied. So in those situations, all you need to do is you start by calculating the reactions and then you work out what the bending moment is. It can get a little bit trickier if you don't know where the point of maximum bending moment is, such as in the worked example. But you're just introducing one extra step in that scenario. So you calculate the reactions, you then determine your position of zero shear, so you clearly need to understand what shear forces are, and then you can calculate your bending moment at that point. And that's it really. Even in more complicated scenarios, assuming that your situation is statically determinate, then you follow exactly the same process. I hope you like this video. I'm that structures man. And if you do like it, please click like or subscribe. Thank you.